4.3 The Poisson Distribution. The objectives of this video are to define the Poisson distribution, calculate the probability of outcomes using the Poisson distribution, and estimate the mean and standard deviation from a sample that approximates Poisson distribution. Examples of Poisson distributions are the number of calls coming per minute into a call center, the number of cars arriving at a traffic light within the hour, the numbers of births expected during the night in a hospital, the number of typographical errors found in a book, the numbers of hurricanes in a given season, or the numbers of hailstorms in San Angelo during a year. Well, let's have a look into the characteristics of Poisson distribution. So Poisson distribution is applied in situations when we have a large number of independent Bernoulli trials. So n is very large, and the probability of success of one of those Bernoulli trials is small. So when n is large and p is small, the probability mass function depends almost entirely into the mean, np. np is the mean of the binomial distribution, remember, and very little on the specific values of n and p. So for that reason, we are going to define a variable lambda, and lambda is equal to n multiplied by p. Let's review the binomial random variable probability mass function, mean, and variance. So remember, we said that x is distributed as binomial with n parameters and probability of the Bernoulli trial equal to p. Then the probability mass function for the binomial is defined in terms of the binomial, which is the number of successful trials, multiplied by p to the x and multiplied by the probability of failure 1 minus p to the n minus x, where x takes values from 0 to n, so there are finite values, and 0 otherwise. The mean of the binomial distribution is n multiplied by p, and the variance is n multiplied by p multiplied by 1 minus p. In the Poisson distribution, n approaches infinity, so to compute the mean and the variance, we need to apply the limit with n approaches to infinity. Before doing that, we need some preliminary results. Now I'm going to compute these two limits and use those limits in the next slide to compute the mean and the variance. Now the limit of 1 plus x over n to the power of n is equal to the limit when n approaches infinity of, I'm going to apply the exponential and natural log function, so they will cancel out to each other, but it will help me to compute this limit. So e to the natural log, they cancel out, of 1 plus x over n to the power of n. Now, because we have the natural log of something to the power of n, so I can move the n to multiply. So this is equal to the limit where n approaches infinity of e to the n multiplied by the natural log of 1 plus x over n. And this is equal to e to the natural log of 1 plus x over n divided by 1 over n. I just move n to the denominator, so I have to move it as 1 over n, so it's equal to the previous one. Now, if I want to apply the limit at this point, 1 over n is undefined, so I cannot apply the limit at this point. So the usual trick is to apply the L'Hopital rule. What we do is we derivate numerator and denominator. So the derivative of the numerator is the derivative of a natural log of something multiplied by the internal derivative. So the derivative of natural log is 1 over the argument 1 plus x over n, and the derivative of the internal derivative, so it's the derivative of a constant, and the derivative of x over n. We are derivating with respect to n. So in this case is x divided by n squared, and divided by the derivative of the denominator, which is again 1 over n squared. Now, if you notice, we have 1 over n squared in the numerator and denominator, and it will cancel out. So the limit when n approaches infinity of e to the x divided by 1 plus x over n. And now we can apply the limit. So when n approaches to infinity, this is 0. And so therefore we have x divided by 1. In conclusion, the limit when n approaches infinity of 1 plus x over n to the power of n is equal to e to the x. The next step is to calculate this limit. So to start, I'm going to expand the numerator in such a way that I can cancel this factorial in the denominator. So this is equal to the limit when n approaches infinity of n multiplied by n minus 1 multiplied by n minus 2 and so forth until n minus x plus 1, and then we have multiplied by n minus x factorial. So all the terms or the next terms are included there, divided by n minus x factorial multiplied by n to the x. So we can see here that n minus x factorial cancel with this n minus x factorial. Now what we are left in the numerator is with a polynomial. So we have 1, 2, 3 up to x terms. So on the numerator we have x terms. So the polynomial in the numerator is going to be the maximum exponent, it will be x. Let's see how can we expand that. So if I start by multiplying the first two terms, so I have n multiplied by n is n squared, and multiplied by negative 1 is minus n. These are the first two terms multiplied by n minus 2 up to n minus x plus 1. So then next we have to multiply these two terms. So if I multiply those two terms, so I have n cubed minus 2n squared minus n squared minus 2n, and then that multiplied, the following term will be n minus 3 up to n minus x plus 1. So now the first term is n cubed minus 3n squared minus 2n is order 3. Now multiply by n minus 3 n minus x plus 1. So if I keep doing, the result in this case will be a fourth order polynomial. So that will be n to the 4 plus or minus 3n cubed, and then I have to multiply this by all these two terms. So I have to keep going, and then I'll multiply by n minus 4 up to n minus x plus 1. So what we can see is that every time that I expand it with a new term, the exponent is growing. So it will grow depending how many times we have to multiply. So because we have x terms here, so the maximum exponent, it will be x. the final expression will be something like this: n to the x plus a multiplied by n to the x minus 1 plus b multiplied by n to the x minus 2, and the last term will be a constant. So it's an x-ordered polynomial. So if I go back and replace that in that expression, we have the limit with n approaches to infinity of n to the x plus a multiplied n to the x minus 1 plus b n to the x minus 2, and so forth until we have a constant c, and in the denominator we have n to the x. Now we can separate all the terms, all of them divided by n over x. So we have n to the x divided by n to the x plus a multiplied by n to the x minus 1 divided by n over x plus b multiplied by n to the x minus 2 divided by n over x plus, and so forth until the last term is c divided by n to the x. Now, what is this limit? In the first case, it will cancel out, so we have 1. In the second case, we have n to the x minus 1 divided by n to the x, so this is a divided by n. When n approaches to infinity, 1 over n is 0. So that will be 0. And all the other terms will be the same. So in this case, n to the x minus 2 divided by n over x, it will result to 1, or b divided by n squared. When n approaches infinity, that will be 0. And so there will be all the other terms. So the final answer of this limit is that the limit is equal to 1. Now we're ready to compute the probability distribution for a Poisson distribution. Remember that a Poisson distribution is a binomial distribution in which n is a very large number. So we need to apply the limit to the probability distribution of this binomial. Remember, the probability is given by the binomial part from n choose x, p to the x, 1 minus p to the n minus x. So if I expand this binomial, I have that this is n factorial in the numerator, and the numerator is n minus x factorial multiplied by x factorial and multiplied by the probabilities. Now, I'm going to write this expression in terms of lambda. Lambda is equal to p multiplied by n, so p is equal to lambda divided by n. So I'm going to replace p in this expression and also apply the limit. So we have that the limit when n approaches infinity of p of x is equal to the limit when n approaches infinity of n factorial divided by n minus x factorial multiplied by x factorial in the denominator, multiplied by p, which is lambda over n to the x, and multiplied by 1 minus p, which is 1 minus lambda over n to the n minus x. Okay, in the next step I'm going to do two things. I'm going to swap these two terms, and I'm going to divide this term into 2. So the first thing is the limit when n approaches to infinity of n factorial divided by n minus x factorial and multiply by n to the x. I'm taking this term. Lambda to the x divided by x factorial. And the last term, I'm going to divide it in 2. So the first one is 1 minus lambda over n to the power of n multiplied by 1 minus lambda over n to the power of minus x. Now we are ready to apply the limit from the previous results, we have this limit, and that limit is equal to 1. So the first case is equal to 1. Then we have lambda to the x divided by x factorial. Then we have 1 minus lambda over n to the n. So we can use this result. We have this limit written in terms of x, and in our case is written in terms of minus lambda. So we have minus lambda, so this limit will be minus lambda. So this is e to the minus lambda, and in the last case we have the limit with n approaches infinity, so this is equal to 0, so it's equal to 1. 1 to the minus x, so that's 1. Therefore, the limit when n approaches to infinity of p of x is equal to lambda to the x divided by x factorial multiplied by e to the minus lambda, and this is equal to the probability of the Poisson distribution. The Poisson distribution. And is written in terms of lambda. P of lambda, we call it. Summarizing, we said that x is distributed as Poisson with parameter lambda, and the probability mass function of x is given by e to the minus lambda multiplied by lambda to the x divided by x factorial when x is equal from 0, 1, and so forth, and 0 otherwise. This is still a discrete variable because it takes only the integer values. The mean of the Poisson distribution, mu of x, is given by lambda, and the variance of the Poisson distribution is also given by lambda. To highlight, x is a discrete random variable, and lambda must be a positive constant.